welcome to Chapter 4, Solving Easy Trig Equations. Okay, so what we want to do is take a look at these simple equations. They all look like this. They give you a ratio, for example, 1 to 2, and they give you a function. What they don't give you is the angle x, or sometimes they may call it theta, or they may call it x. It doesn't matter. The point is they give you some ratio, and they ask you to find all possible angles for which the sine function gives you that ratio, for example, or they may give you cosine or tangent, cosecant, whatever. Anytime we see an equation like this, we will call it easy kind of trig equations. And what we're going to do is develop a little strategy that will help us take one step at a time and make them all really easy. They will be easy. That's why it's called the easy trig equations section. Okay, the strategy will go something like this. They give you a simple equation. First of all, check that it is a simple equation. If it's not, sometimes you may be able to tweak it just a little bit to make it look like a simple equation. For example, if they give you cosecant is 2, you may be able to tweak that to say sine is 1/2. Or if they give you sine x equals tangent x, you may be able to tweak it so that you get tangent x equals 1, or I'm sorry, sine x equals cosine x. You may be able to tweak that to rewrite as tangent x equals 1. Anyways, this strategy will be good for this type of equations. If it's not this type of equation, you may have to need a different strategy. You may need a different strategy. So that's for starters. Make sure you got a simple equation. Second, what you do is you graph the function. By now, we're experts at graphing functions. There's your sine graph, just like that. You should be very, very comfortable with graphing the sine, cosine, tangent, secant, cosecant, all those simple functions. And that's our first step. You graph the sine function. The second step is you graph the ratio that's given. In this case, we're saying sine x equals 1, so the ratio is 1. Graph that, y equals 1. And then that's it. You're looking at the solutions. Everywhere where those two graphs meet, at every single value of x, sine x equals 1. So you may want to just take a moment to point at the solutions. They're there. Easy. Also note that these solutions will go on forever to the right and to the left. Some books, as a matter of fact, will just have you find the solutions between 0 and 2 pi. What we're going to do is try to find enough solutions to where we can recognize the pattern and use that pattern to describe all possible solutions. Here we've just got 3. There are millions more. That leads me to the next part of the strategy, that is to actually list the solutions. Often, your list will look something like this. It'll just list a few angles, and sometimes you write etc, etc, etc. Other times we cook up a little formula that describes all of them at once. In fact, that's probably the most common way to do it. So we're going to do this example in a little bit more detail, and I hope that at least this part serves to lay out the strategy. 4 simple steps. Graph the function, graph the ratio, point at the solutions, and then start listing the solutions. Okay, let's take a look at that example where we will take it apart just a little bit more. First thing we do is graph the function. That's easy, graph sine x. Next thing we do is graph the ratio. In this case, the ratio is 1. The next thing we do is point at the solutions and say, hey, they're staring at us right there. Those are the solutions. Those are the guys, those are the x's for which sine of x equals 1. And keep in mind that there's a whole bunch more to the right and to the left. We just want to point out enough to where we can see the pattern that will help us describe all of them, every single solution. I think this is enough for the pattern to figure these out, which takes us to the next point. We actually want to list them. To list them, what we want to do is look at their position with respect to the rest of the graph. For example, this one's right smack in the middle of these 2 points. If we can figure out what those 2 points are, then we can figure out which point is right smack in the middle of them. As a matter of fact, I think those 2 points are negative 360 and negative 180. Or in radians, it'd be negative pi and negative 2 pi. You could just have to think about it for a couple of seconds and you can figure out the midpoint. And that would be negative 270 degrees. Or in radians, it would be negative 3 pi over 2. And that's it. That's how we list these. Well, sometimes. Other times, it may not be quite as easy. You may need to use your excellent knowledge of famous angles or famous triangles, like a 30-60. Other times we may need a calculator. Anyways, for now let's go on to the next one. This one's right smack in the middle between 0 and 180. 0 and 180. 180 and 0. And it's right in the middle of it. That forces it to be 90 degrees or pi over 2. And similarly, this one's between 360 and 540. That forces it to be 450 degrees or 5 pi over 2. Then you can just write it this way, negative 270, and I wrote etc., because to the left of that there are many more. And then I note the pattern here. If I move 360 degrees to the right, I get to the next one, which is 90 degrees. And if I move 360 degrees more, I get to the next one, which is 450. And on and on and on and on. And this would be an acceptable way to list all the solutions. While it's acceptable, it may not be preferable. Most people would prefer a way to describe them. It's sort of like a little machine that generates all of them at once. And that machine is this equation here: x equals 90 degrees plus any k multiple of 360 degrees for all k that are integers. That's what that last part means. In other words, whole number k's. Any whole number that's positive or negative. And by putting various values of k in there, you can sort of generate every single possible solution. And in a nutshell, that's it. That's how we solve these easy trig equations. Again, not much to it. You graph the equation, you graph the ratio, you point at the solutions, and you list them. Clear? All right, let's take a look at another example. This time, let's practice with a little cosine. First thing we do is graph the function. There it is, cosine graph. Next thing we do is graph the ratio. In this case, it's -1. Next thing you do is point at the solutions. There, and there. There are the solutions. And the next thing you do is just list them by noting their position with respect to other parts of the graph. And you get 180, -180, 540, etc., etc. Again, this pattern is easy to recognize. They're all one period apart, meaning 360 degrees. So you would write -80, 180, 540, etc., etc. Or you could write, start off with 180 and then go from there any multiple of 360 degrees to the right or to the left. Well, that's not the only way to say it. You could also say start off with -180 degrees plus any k times 360. That would be acceptable as well. That was example number 2. Maybe we can take a look at another. This time we're going to practice with cosine x equals 0. First thing we do is graph the cosine function. Done. Next thing we do is graph the ratio. Done. See, this is where it's sort of better to do this with mechanical hands than the real hands. There's no way that the real hands can graph this fast. Watch how fast these things point at the solutions. Point at the solutions. Go. Whoa. Next thing, list all the solutions. Well, again, we're going to use common sense to list all of them. For example, that point right there is 0 degrees, that point right there is 180 degrees, and our solution is right smack in the middle of them. That's got to be 90 degrees. Note that that's pi, that's 2 pi, right in between you got 3 pi over 2 or 270 degrees. And on and on and on. Pattern is easy to recognize here as well. They're all 180 degrees apart, or pi radians apart. So you would describe the solutions as 90 degrees. X could be any 90 degrees plus a multiple of 180, an integer multiple of 180, that is. Or in radians, a similar thing. And that's it. Let's take a look at, we're on a roll now, let's take a look at another example. Maybe we do a little tangent this time, man. Maybe a non-famous ratio, something weird like -2.75. Just to see if you're scared of that. You should be scared. There's nothing to it. Let's follow the procedure. You graph the function. There. We're experts at graphing tangent right now. You graph the ratio, -2.75. There. Done. This is so easy. I'm doing this with my left pinky. I don't even need all my hands to do this. Let's point at the solutions. There. And let's list them. Alright, here maybe we have to slow it down a little bit. How would you actually list them? Let me talk about that extensively for hours and hours. No, I'm going to talk about it for a couple minutes. Let's keep the following in mind. If you take your calculator and you punch in their tan inverse of -2.75 and you hit the equal mark, you'll get about -70 degrees. assuming that your calculator is in degree mode. Now, I'm looking at the picture. I've got 3 solutions up here, and there are millions more. But the calculator is only giving me one. The one that's between 0 and negative 90 degrees. Why is that? Why doesn't it give me all the other ones? Well, the truth is that the tan inverse function was never designed to do that, nor was your calculator. So maybe this is a good time to get it all straight. The calculator will only give you that value right there. This value over here will never be given by the calculator. It just doesn't work well there. Nor here. And the truth behind, I'm sort of simplifying things, but behind this simplification is a long, long story about functions and one-to-one functions and which functions are invertible and how we tweak these tangent functions to become invertible functions. But this discussion is probably best suited for either algebra class or a pre-calc class. At this point, I really want to stay focused on solving these equations, these easy equations. So for now, suffice it to say that the tan inverse function on the calculator will only give you values right there in the middle between negative 90 and positive 90 degrees. So that's the only one that the calculator will give you. From there, our job will be to find the other ones using common sense and symmetry of the graphs. Okay, so let's go back to, oh wait, no, let's not. In fact, let's talk more about the other inverse functions. The tan inverse will go from negative 90 to positive 90. The sine inverse will also be given between negative 90 degrees and 90 degrees, while the cosine inverse gives you values between 0 and 180 degrees, when these exist. Okay? Keep that in mind. Calculator lives happily here in each one of these regions, and they don't do much outside of these regions. Let's go back to our solution here. We found that this is approximately negative 70 degrees. How are we going to find the other ones? Well, we're going to use common sense, and we're going to note that they're all spaced in the same length from each other as the sine is a tangent graph, and that tangent graph is spaced 180 degrees apart. That tells you exactly how to find the other ones. You would just take your negative 70 degrees and add multiples of 180, and that's it. That's how we solve this one with a non-famous ratio. Alright, now let's do this very important example, cosine x equals 1/2. The reason it's very important is because the pattern will not be as easy as the previous patterns. If you recall, the previous patterns were all the solutions were nicely spaced apart, either 360 degrees apart or 180 degrees apart. This one's sort of a curveball, a big curveball, just like that. You graph the ratio, you graph the function, you point at the solutions. There they are, a whole bunch of them, and you start to list them. And again, this pattern is different than the other patterns. So let's think. Cosine x function, well, first, you can't even begin to see the pattern if you can't even find one solution. So let's at the very least find the first solution. In this case, because the ratio is a Fabit's ratio, 1/2, you could think to yourself, just using common sense, I've got an angle x that I'm trying to find, and I know something about that triangle. I know that this adjacent side is 1. Whenever the adjacent side is 1, the hypotenuse is 2. And think to yourself, do you know that triangle? Is that triangle famous? And the answer is yes. It only happens once that in a triangle, one of the sides is half the hypotenuse, and that happens for a 30-60 triangle. And in that case, the angle across from 1 is the shortest one. That one's got to be 30 degrees. And that forces the complementary angle to be 60 degrees. And that tells you exactly what x is. X is 60 degrees. That's one way to find the first one. The other way to find that angle would be to use your calculator and realize that cosine inverse function will give you angles between 0 and 180. This will give you 60 degrees. You want to use the calculator whenever this ratio is non-famous. Either way, on the graph, this is the solution we just found, x equals 60 degrees. Okay, and that's the only one that we're going to get from the calculator from the famous triangle. In fact, that's the only one we need. From there, we can find all the other ones using common sense. So let's go back to this. This is the one we found, 60 degrees. Now, see, the pattern's not as clear as the other ones. That's why this is such an important example. You really can't go 180 degrees either way and find a solution. what we're going to do is skip solutions. We'll skip one, and we find that the following one, that one is exactly 360 degrees apart. Just from the symmetry of the graph and the fact that the cosine graph has period equal to 360, we know that that distance got to be 360 degrees. And we sort of start to distinguish these solutions. The distinction will be the solutions that occur downhill and the solutions that occur uphill. These ones that we're pointing at right now, those are downhill solutions. And those, in fact, do have a nice pattern to them. They are all 360 degrees apart, every one of these downhill solutions. So you could sort of put them in different buckets, the uphill and the downhill solutions. And you could say, hey, all the downhill solutions, they're all like this. They start off at 60 degrees. And from there, you can add or take away multiples of 360 degrees. And that's great, but I think we missed half of them. So let's go back and think about how we can figure out the uphill solutions. Well, using the symmetry of the cosine graph and the fact that cosine is even, you know, whenever cosine of 60 is equal to whatever, cosine of negative 60 will be the same. That's from the famous identity sheet, the cosine is even. Or just from looking at the graph and the symmetry. If the distance from 0 to the right is 60, then the distance from 0 to the left is negative 60. And that helps you find the first uphill solution. From there, well, they're all equal. These have a nice pattern. All the uphill ones are 360 degrees apart. So you could say the uphill solutions are 360 plus multiples of 360. And this would describe a complete set of solutions. And we're done. Again, this was a very, very important example because the pattern was not as clean or simple as the other ones. We sort of had to separate the solutions into two bunches, the downhills and the uphills. And that got us to where we could easily describe the solutions. Okay, maybe we can take a look at another one of these uphill, downhill business. So in this case, I'll take a non-famous ratio like 0.57. First step is easy. Graph the sine function. Graph the ratio, negative 0.57. Point at the solutions, easy. With my pinky I can do it. List the solutions. This is where it gets interesting. So how we're going to do that? Well, we're going to use a calculator because this is a non-famous ratio. And the calculator will give us one solution, the one that's between negative 90 and positive 90. Looking at the graph, you should be able to see right there which solution it's going to give us. It'll give us that one right there, negative 34.75 degrees. And just thinking about it, is that uphill or downhill? You guessed it, that's an uphill solution. And there is a clean and easy pattern for all the uphill solutions. They're all 360 degrees apart. And then there's a little bit more fun coming up. How we're going to find the downhill solutions. That requires close attention. Let's think. This is the one the calculator gave us, negative 34.75 degrees. You got to use common sense here. This distance from 0 to pi, that's 180 degrees, clearly. And that distance from the 0 to the left, where the solution was, that one was 34 degrees, 34.75. So using the symmetry of the graph, you would expect this distance right here to be exactly the same, 34.75 degrees. In fact, it is. So do the math here. You take 180 degrees plus the 34, that gives you 214.75 degrees. And that's one of the downhill solutions. Got it? If you didn't get it, just rewind it again and again and again. We'll say exactly the same thing over and over again. Alright. Okay, so that gets us here where the downhill solutions are complete as described. That about completes it. This was a really nice example because you had a non-famous ratio like negative 0.57, and you had not exactly a trivial pattern. We had to separate them into the uphill and downhill, and that makes the patterns easy. They're all 360 degrees apart. That completes this section. I hope that you will find this helpful in completing the homework. We will see you back soon for solving more trig equations. We're going to step it up a notch or two in the next section. Maybe solve some that are just slightly above easy trig equations. Okay, hope you found this helpful. We'll see you back here soon. bye.